This is Professor Derek Seitz. Graphs, polar plane. How can we visualize rotational relationships? We'll find that we can use ordered pairs that involve distances and angles, and then introduce equations. This picture here shows some concentric circles on these various cones here. Polar plane concepts. The polar plane has a central pole or origin and a horizontal polar axis. Ordered pair relationships are represented by points with coordinates r, theta. R is the directed or signed distance to the point from the pole or the origin. Positive values extend on the terminal side of the angle theta. Negative values of r extend in the opposite direction from the positive values. Theta is the directed, signed, positive or negative, rotation to the point. Positive values for theta are counterclockwise rotations, and negative values are clockwise rotations. A concentric circular grid facilitates placements. Here we see the polar plane, the pole, the origin here, and along the horizontal is the polar axis. To plot points, you have to know the coordinates. The r, the distance, directed or signed distance from the pole to the point, and the angle of rotation from the polar axis to get there. Our first point here is 5 pi over 6. We're showing here degrees of 30 degrees for this angle theta for this point. And there are two angle systems of measurement that you will learn about when you study trigonometry. That's one we're most familiar with in common everyday life is degrees, but the mathematical one uses parts of a circle, and it's called radians. So pi over 6 is the same in the radian measure as 30 degrees. You have 360 degrees all the way around in degrees measure, and you have 2 pi all the way around in the radians measure. So there's 5 pi over 6, that point there. Let's look at the other points. 3, notice that it's on the third circle, concentric circle out, the grid here. 3 and pi over 4, which is a 45-degree angle. 4 and pi over 3, it's a 60-degree angle. 5 and pi over 2, that's a 90-degree angle. 4.5 and 3 pi over 4, that's greater than 90 degrees. Now you're rotating over into this sort of the second quadrant here of this polar grid. 0, 0 is the pole. 5 pi is over here. So pi is halfway around the circle, and 5 is the r, stands for radius here. And these other points, 4.4 and 7 pi over 6, and this one here is of interest, -4 and pi over 3. The positive 4 and pi over 3 is this point up here. When you make the r value negative, you go in the opposite direction from that point and end up down here. So that's a -4 pi over 3. You rotate, but then flip the r to the other opposite direction. Down here, a 5 and 3 pi over 2. Here's a 2 and a -pi over 6. So this shows you how you can place points using the coordinates that are a distance, a sine distance, and an angle, a sine angle. Remember, the positive angles rotate this way, and the negative ones rotate this way. That's why this point here is of interest. Notice it's 2, but look at its angle, negative pi over 6. So it rotated in a negative down to here. These other ones are positive values for theta. Here's a negative rotation with 2, puts you right there. You introduce equations, it brings order. The solutions of equations in the variables r and theta illustrate relationship patterns. A solution set is all the ordered pairs r theta that make the equation true. If you take the value of r and substitute it in the equation for r and the theta for theta, you get a true equation. Equations maintain equality relationships. Equality relationships are balanced relationships, and balance brings order. Here we have an equation of a polar line. All the points that solve this equation are all lined up on this line. It's a very order, it's continuous, there's no breaks in it, and it's smooth, there's no sharp points or anything. And there are now infinitely many points in this graph. What is the equation? Theta is pi over 3. Pi over 3 is 60 degrees, and we're going with pi over 6's here for the wedges. Pi over 3, it doesn't matter r, any r, as long as you have pi over 3 rotation, you get a line. For this particular notation here, we say r can vary between negative infinity and positive infinity, off that way or down that way. It's a line, it doesn't end here. This is just where the graph border is cut off. A polar circle. Simple equation. R equals 3. In this case, as long as r is 3, it doesn't matter about theta, you get a circle. Again, infinitely many points, continuous, smooth, orderly. Theta here, we're only varying it between 0 and 2 pi. One time around, you get the circle. If you go any more, it'll just keep overriding itself, and it'll look still like a circle, even though there are other points, because you can have ordered pairs that have more than one rotation around. Here we have an equation that produces polar petals. The equation is r equals 3 times the cosine of 4 theta, where theta varies between 0 and 1 revolution around the polar plane. And these are all the points that make that equation true. Again, cosine is a function that you'll study in trigonometry, and it's inherently involved in circular kinds of behaviors. It's even called a circular function. But look at this amazing pattern from this simple equation in this polar plane coordinate system. Polar spiral. This is called a logarithmic spiral, and its equation is r is equal to little e, which happens to be the irrational number, a famous number like pi, that's the base of natural logarithms and natural exponential functions. Little e, it's approximately equal to 2.718. Anyway, little e to the theta divided by 5 power. This equation here, and for this graph, we're varying theta between 0 and 6 pi. That's 3 revolutions around. So we get 1 revolution, 2 revolutions, 3 revolutions. If we allow theta to go infinitely far, this thing would just continue going down and down and around and around. But look at the amazing order that you get out of this simple equation in this polar plane. Let's look at a point here, 5 pi over 6. You can construct a right triangle, 90-degree angle, and we have a 30-degree angles here for theta. The polar coordinates are theta, I've already told you 5 pi over 6. We want to know, what about the rectangular coordinates? If we were in a rectangular grid system, like in the real number plane, what would the coordinates be there? And here's the relationship. The x is equal to r times the cosine of theta. And that's because the cosine of theta is defined to be x over r. And the y is r times the sine of theta. Again, these are basic trigonometric functions, and you can express x and y from them in terms of r and theta. Also, note here the Pythagorean theorem that x squared plus y squared will equal to r squared. So we have down here r squared is x squared plus y squared. And also of note, using trigonometry, is that the tangent of theta, which is the opposite over the adjacent, y over x, that's another relationship we see here. And of course, x can't be 0 for this. If x is 0, then theta will be pi over 2, will be a 90-degree angle for that to happen. So these show the relationships that you can convert between polar and rectangular coordinates. For our particular example here, the rectangular coordinates, 5 is r, pi over 6 is theta. So the x here is 5 cosine pi over 6, and the y is 5 sine pi over 6. And you get the same point if you're in a rectangular grid system. Let's take an example of polar to rectangular spiral example. We saw the polar equation r equals e to the theta over 5. Let's convert this to an equivalent equation in the rectangular coordinate system, placing r by the square root of x squared plus y squared, because remember r squared is x squared plus y squared, and we get this. Step, take the natural log of both sides of this equation, and on the right, the natural log and the exponential base e are inverses. They undo each other, so you just get theta over 5. The exponent is the result of the right-hand side. Multiply both sides by 5 and swap sides. Theta is 5 times the natural log of square root of x squared plus y squared. Then take the tangent of both sides of this equation. The tangent of theta is the tangent of the right-hand side. And we learned that the tangent of theta is y over x. So y over x is equal to that. Multiply both sides by x, and you get this equation here, which doesn't have r or theta anymore. It only has x and y's. And when you graph it using a graphing tool in the real number plane, you get this graph here. This is a logarithmic spiral. And we have it spiraling down and down and out and out. And it goes infinitely small and infinitely large. An alternate example for that same conversion is interesting that we'll look at here. Beginning with r equals e to the theta over 5. Again, r is the square root of x squared plus y squared. Natural log of both sides, like before. These cancel out, they're inverses. Multiply by 5, you get down to this step. Now at this point, take the cosine of both sides. Then multiply both sides by r. We know that r cosine theta is x. So we place this by x, and we know that r is the square root of x squared plus y squared. So now we end up with this equation here. It's quite an involved equation. X is the square root of x squared plus y squared times the cosine of 5 times the natural log of the square root of x squared plus y squared. But there's no longer any r's or thetas in it. And when you graph it, you get a double logarithmic spiral. One spiral spiraling this way, and another spiral spiraling this way. Why do you get a double one here? Because this conversion was not totally equivalent. It ended up with something. Notice in our final formula here for x, or our final equation, that if xy is a solution to this, which means it's a point on the graph, notice that x and negative y will also be a solution, because if you replace y with negative y, you're squaring it. Whatever you put in here squared, you're going to get the same positive answer. And so if you leave x alone and put a negative y in, that means, but what is, if you have xy as a point and you also have x negative y, that's a reflection across the x-axis. And you can see that the second spiral, or whichever one you want to look at, is a reflection of the other one across the x-axis.